This building is the headquarters of CCTV, China's main state-owned television broadcasting network, and is located in Beijing and includes administrative offices, newsrooms, broadcasting rooms, program production rooms, and studios. At the time, Beijing was undergoing a massive urban redevelopment project ahead of the 2008 Olympic Games, which required a new landmark building. In addition, the existing CCTV headquarters was struggling to keep up with the latest broadcasting technology and efficient operations due to its aging facilities and remote space, and required a new headquarters that would incorporate the latest broadcasting technology, provide a variety of broadcast studios, and ample office space. The project was therefore undertaken by Lem Koolhaas and his architectural firm OMA. Dutch architect Lem Koolhaas is one of the most influential architects in contemporary architecture, known for his innovative and experimental designs. His major work includes the Seattle Central Library, Casa da Musica, and the Rotterdam. His work often reflects a specific social and cultural context, and he believes that architecture should function as a social phenomenon, not just a building. These characteristics of the architect are also reflected in the CCTV headquarters. The CCTV headquarters is about 234 meters tall, with 51 floors above ground and 3 underground, consisting of 2 towers tilted at 6 degrees, joined by a 75-meter vertical cantilever. The shape is similar to a prehistoric dolmen. The construction of dolmen required a great deal of labor, and the larger the dolmen, the greater the authority and power of the group. With the CCTV headquarters building, Lem Koolhaas wanted to show the world that China had emerged as the world power through the Beijing Olympics. And instead of these designs competing for ultimate heights and style within a traditional two-dimensional tower that soars toward the sky, CCTV's loop provides a truly three-dimensional experience, culminating in a 75-meter cantilever. However, due to this unique design, structural instability caused by the concentration of loads at one end has to be addressed. In addition, CCTV is located in the central business districts of Chaoyang District, Beijing, China, which is located in the middle and lower reaches of the Yongding River, which has weak soils and uneven grounds. Consequently, a piled raft foundation was chosen, followed by the bottom-up construction method, starting from the underground structures and progressing upwards. The process began with a soil investigation, evaluate the ground conditions and determine the optimal locations and depth for the piles. Once this assessment was complete, excavation commenced to reach the necessary depth for a stable foundation. During excavation, diaphragm walls were installed to prevent soil collapse and ensure stability. Upon completion of the excavation, piles with a diameter of 1.2 meters and a length of 52 meters were driven into the ground. These piles served to transport the building's load to deeper, more stable soil layers. Following the pile installation, the left foundation was constructed atop the piles. The left foundation works in conjunction with the piles to evenly distribute the entire building loads, mitigating the risk of punching shear failure, which could occur if only piles were used due to their small cross-section area. After installing the piles, rebar was placed in the left foundation and concrete was poured. HRB 50 grade rebar was used for the left, with the lower section reinforced with 2 to 7 layers of mesh and the upper section with 2 to 3 layers of mesh. The concrete pouring for Tower 1 took 52 hours with a total volume of 39,000 cubic meters. For Tower 2, the concrete pouring took 54 hours with a total volume of 33,000 cubic meters. The total volume of concrete poured for the base plate exceeds 120,000 cubic meters. During the massive concrete pouring process, crack control is the critical aspect. To address this, CCTV implemented two key methods. The first method involved increasing the proportion of fly ash in the concrete mix to 49%. Fly ash enhances the workability of concrete, reduces shrinkage, prevents shrinkage cracks, and lowers the heat of hydration, thus preventing temperature-induced cracking. The second method included using a combination of plastic sheets, 3 layers of straw mats, and 1 layer of canvas for insulation and maintenance. Additionally, a large capacity concrete computer temperature monitoring system was employed to measure the temperature in real time. Maintaining appropriate temperature and humidity levels while the concrete gains initial strength is crucial for preventing cracks, and this method effectively ensures this. We also used pipe cooling to control internal heat generation during this process. This measure prevented the concrete from cracking and created a solid foundation. The cantilevered portion of the CCTV required a different construction process that of a conventional two-dimensional skyscraper. Therefore, ARUP considered a total of 3 methods to construct the cantilever. The first method, which is considered, was the temporary tower support method. This method uses temporary towers to support the structure while the cantilever of the building is constructed. This temporary tower provides the necessary support until the cantilever has achieved structural stability on its own. After that, the temporary tower is removed. Example, thin and long structures cannot resist bending moments on their own, so this method is used not only in bridges but also in buildings with long and thin structures such as bridges. However, in the case of CCTV cantilever, it is very thick and heavy, so there is a problem that it requires a strong and large temporary tower that can withstand a large load. Designing a temporary tower that could withstand a large load was not easy in itself, and even if designed, a lot of labor and cost were required to install, maintain, and remove the temporary tower, so a method other than this method was needed. The second method considered is the lift-up prefabrication method. In this method, the cantilever portion of the building is manufactured in a factory as large-scale modules, which are then transported to site and installed using a crane. Only assembly work is mainly performed in-site. This method has the advantage of significantly reducing on-site work time and ensuring quality because the modules are manufactured in a highly controlled manufacturing environment from external conditions such as weather. The Amada Sky Building's floating garden is a representative example of construction using a method of manufacturing modules and then lifting them. This building is located in Osaka, Japan, and is especially famous for the floating garden located at the top, a characteristic structure that connects two towers. The Amada Sky Building floating garden consists of an observation deck and a relaxation area for visitors. It was stubborn to use prefabricated modules because the internal structure was relatively simple and did not require additional heavy or complex equipment. However, in the case of the CCTV headquarters building, the cantilever part is structurally complex because it accommodates the broadcasting studios and officers. This results in increases costs and technical difficulties in module production. Additionally, the complex structure also increases the weight of the module. This causes additional problems such as the transportation cost of moving modules from the factory to the field has increased, and the process of lifting and assembling heavier modules has become much more difficult. So with method did all adapt to solve the problems of the first and second method. The method ultimately adapted for cantilever construction of the CCTV headquarters building is the balanced cantilever method. First, let's check the process of this method through a 3D modeling that we created ourselves. As you can see during cantilever construction, a horizontal member is supported through a diagonal member and construction of two independent cantilevers is carried out. In this process, a lowest part of the cantilever meets first, and then construction of the remaining part processes. This method is easy to adjust on site and can more accurately meet the design requirement of complex structures through a gradual construction process. Additionally, because it supports its own load, much less temporary structures are used compared to method 1, and because both cantilevers are constructed on site at the same time, it takes less time and costs less in terms of transportation and crane operations than lifting complex and heavy modules using method 2. In other words, we were able to solve the problems of the first and second method by conducting construction using the balanced cantilever method through accurate calculations. However, challenges remain to be addressed with this approach. If constructed this way, the two cantilever must engage exactly in the center. However, the metal members used during construction have distinct thermal expansion and contraction effects which generate stress. This is the main factor stopping the two cantilevers from meeting exactly in the center. Let's take a look at how this problem was solved. First, in order to effectively manage these thermal expansions, contractions, stresses, and to achieve optimal structural alignment, expansion joints were used to connect the tower and cantilever. Expansion joints provide the necessary flexibility at the connection points of structures during construction, allowing them to withstand expansion and construction due to temperature changes. This plays an important role in minimizing the negative impact of heat-induced deformation on structure stability. Additionally, when the cantilever structures extending from both sides meet in the center, they are connected through 7 links. This connection was made by a pin joint. Pin joints allow rotation of members but limit horizontal or vertical movement. By connecting the 7 links with pin joints, each tower is designed to respond independently to loads by supporting it horizontally and vertically but also allowing rotation. When constructing high-rise buildings or complex structures, wind can be a big variable. Wind places additional dynamic loads on structures and can affect the safety of construction equipment such as cranes. Therefore, construction of the CCTV headquarters building was carried out in a morning and a windless day to minimize movement of the structure and ensure maximum construction precision. Morning hours are generally chosen because there is less wind and the atmosphere tends to be more stable. Additionally, since the building's connecting elements and structure joints are directly related to the building stability, their precise adjustment is essential. At CCTV headquarters building, a length of all connecting elements were finally measured 24 hours before ground level. By measuring at the same time the day before, the environment and the day of construction was predicted as closely as possible to maintain connection elements that optimal condition and minimize the impact of environmental changes or other factors on the day of construction on the structure. Tilted buildings, especially those shaped like the CCTV headquarters building, are inherently designed off the vertical axis, resulting in an asymmetrical distribution of loads acting on the building. As a result, these asymmetrical loads generate additional moments and torques due to the effects of gravity. This directly affects the structural stability of the building, making the load of the supporting core even more critical than in a typical building. The tower part of CCTV headquarters has a 6-degree tilted shape. OMA considers the tilted core structure to reflect this tilted shape in the initial design stage to maintain a consistent planar arrangement. However, the tilted core structure has some problems. First, tilted cores resulted in asymmetric load distribution, making it difficult to secure structural stability. This led to the generation of additional moments, resulting in the need for more special materials such as steel and high-strength concrete than typical vertical cores. These special materials contributed to a significant increases in the overall construction cost. Second, when the elevator's travel path was oblique, the passengers' travel time was prolonged and the elevator's operational efficiency decreased. In addition, the technical complexity of the elevator system also increased, adding difficulties to operation and maintenance. Eventually, these rising costs and technical limitations have abundant approaches using tilted core structures. What form of the core did ARUP and OMA solve the tilted form of the building with instead of the tilted core? To create a unique shape, the CCTV headquarters keeps the outer tube structure in an inclined shape, while the core is designed vertically. However, if one vertical core is used here, like other buildings, the tilted structure limits the space where the core can be located. The importance of the core grows further in tilted buildings, which can lead to structural instability. To address this issue, instead of placing one vertical core, we chose to place multiple vertical cores at various heights according to the degree to which the building is tilted. As a result, 7 vertical multi-core with different heights were placed in the CCTV building. In particular, the tower core, bottom core, and cantilever core were properly placed, respectively, as the core is the main factor supporting the load applied to the overhang structure. In this process, auto-climbing system was used for construction workability when placing concrete on the outer wall of the core. Since the cross-section of the core is not constant, a new formwork was needed to adjust to the changes in each cross-section. Therefore, in the part where the cross-section of the core changes, a flexible climbing formwork system was applied that disassembles the formwork and reassembles it according to the cross-section. Each of these cores was designed to efficiently integrate elevators, stairs, air conditioning systems, and power and data wiring. The elevators in the CCTV building has to be located inside the front core while accommodating large amounts of people, so the number of floors and users available were divided. The CCTV building has a multi-core structure that consists largely of Tower Core 1, Tower Core 2, Bottom Core 1, Bottom Core 2, and Cantilever Core, which has a total of 90 elevators arranged in this multi-core. In order to efficiently accommodate a large number of people, a number of double-deck elevators have also been arranged that allowed you to board onto floors at a time. All staircases are integrated within the central core, providing safe evacuation routes in case of fire or emergency. The escape routes are designed for quick access to staircases from each floor and are used in certain areas in parallel with elevators. Tower side core fixed to the ground. This rattle loads as fatal. Especially in CCTV buildings, there was a core without footings in the cantilever part, which required further consideration. So, what method could have been used to solve this problem? The answer was to install the transport truss, which acts as an outrigger. The outrigger system connects the core to a mega column or wall, reducing the moment of the core and holding the displacement. In the CCTV building, they connect the cantilevered core to the exoskeleton in the form of truss. The exoskeleton of CCTV is a diagrid structure. Unlike a regular diagrid, the diagrid is not laid out in a regular pattern, but later at different angles to suit the optimal angle of each section, and more tightly spaced in areas of high stress. The continuous diagrid structure, connected by a butterfly nose, also acts as a continuous loop throughout the CCTV building, allowing stresses in a particular section to be distributed throughout the building. The diagrid structure also allows loads transferred to the tension trusses to be distributed throughout the building. This design allowed the CCTV building to retain its unique cleaning form while providing an efficient and safe internal structure. So how were the members lifted up in the process? The members used for CCTV were lifted through a tower crane. The work area was divided into three areas: Tower 1, Tower 2, and Podium. Tower 1 and Tower 2 were placed with one M1280D tower crane and one M600D tower crane, respectively, and Podium has two M440D tower cranes and one C7050 tower crane, which used a total of 7 tower cranes. The high-rise part of Tower 1 and Tower 2 were equipped with a large tower crane M1280D with a lifting capacity of hundreds of tons, and a medium and large tower crane M600D with a capacity ranging from several tens to hundreds of tons. These cranes had the ability to safely lift heavy components even at high altitudes. Since there was a lot of work in the Podium section that required high accuracy at relatively low heights, two medium-sized tower cranes M440D with lifting capacity of several tens of tons were deployed. Due to the limited space in the Podium section, The C7050 crane with a wide working radius was placed at the center and two medium-sized cranes M440D were placed on both sides of the podium to efficiently utilize the space. However, since the CCTV headquarters building is 234 meters high and the tower part is inclined at 6 degrees, it was not possible to use the method of building the building with a tower crane moving vertically. Therefore, the CCTV headquarters building adopted the method of building the building with two tower cranes. 1. Install tower cranes 1 and 2 on the ground. 2. As the height of the building increases, the cranes move vertically. 3. As the building rises due to the 6 degrees tilted tower, cranes 2 cannot reach end of the building due to the limit of horizontal distance. 4. Therefore, crane 1 is used to dismantle crane 2. 5. Use crane 1 to move horizontally in the direction the building is tilted and reassemble crane 2 in a new position. 6. Crane 1 and crane 2 resume working again. 7. The process involves a total of 14 horizontal movements and 4 vertical movements. In this way, the construction of the tower part of the CCTV was completed. However, since the cantilever structure bore loose significantly from the center of the building, it was not possible for the tower crane to procure it directly. The construction of the cantilever structure was more sensitive to loads and deformations than other parts of the building, requiring high precision and stability, which is why hanging cranes were used. The type of hanging crane used in the construction of the CCTV headquarters was a derrick crane, which is installed on the side of the building and is very flexible. It can be moved and reassembled as required, with all the necessary members for the cantilevered part procured and installed in the exact location.
In previous CCTV buildings, drip and leak problems occurred where water droplets fell from cold water pipes installed above the ceiling. This was a big problem because even a small leak could cause fatal damage if, if it touches broadcasting equipment due to the nature of the broadcasting station. In addition, the previously applied fan coil unit had a problem that it was difficult to respond to structural changes in buildings or changes in use, unlike the characteristic of broadcasting station where the use of each studio can be changed frequently. Therefore, a variable air volume system has been introduced in the newly built CCTV headquarters for the following reasons. VAV systems do not install cold water pipes or condensation drains above the ceiling, which greatly reduces the risk of leakage. This is critical in environments with many sensitive electronic equipment, such as broadcasting equipment. VAV systems provide cooling through airflow, thus preventing this risk of leakage. Outside air can be used for cooling by utilizing the low temperatures of winter and autumn in Beijing. The VAV system can reduce energy consumption and operating costs by introducing this cold external air indoors and utilizing it for cooling. The VAV system provides high flexibility by allowing airflow to be controlled in each zone. When a studio in a broadcasting station is repurposed or a new zone is added, the VAV system can be easily reconfigured to provide the necessary cooling and heating. This enables space optimization. An intelligence controller enables remote monitoring and control of VAV systems, which can check system performance in real time. respond immediately in the event of an abnormality, and manage maintenance tasks efficiently. This reduces maintenance costs and improves system stability and reliability. In conclusion, we introduced a VAV system at CCTV headquarters to enable the protection of broadcasting equipment, energy saving, flexible operation, and efficient maintenance.
Above all, we will conclude the final video of the construction project plan for Team 9. Thank you.